I'm not sure. Okay, it's recording. That's yeah, good. All right, so analytic continuation. And functional equation for QI and some L functions. So there are two issues. Okay, so in general, we have this thing. So this we know that it's convergent for real part of S bigger than 1, right? Originally, real part of S bigger than 1. And of course, the question is why it can be analytically continued to the whole complex plane. That's, for example, even if you use the factorization of zeta k in terms of zeta function and that L function, we don't know how it can be analytically continued. I'm talking about 1 minus 1 over 3s plus 1 over 5s. That's not obvious how to continue that analytically. It turns out that actually there is a method which is modeled after Riemann's proof using theta functions, which works for all number fields. And I'm going to give you an idea of this method, at least in this case, because it's something worthwhile to know. And so this is basically using theta functions. So basically I call lattice theta functions. Okay. So what is zeta QIS? Originally, it was defined to be sum, right? 1 over absolute value of I to the power S, where I is different from 0. But then, because every ideal is principal, so I can write I as something generated by A plus IB for different A and Bs. And we saw that this is actually equal to quarter of sum 1 over m squared plus n squared to the power S over m and n in Z. And this prime means that we exclude, obviously, 0.00. The lattice point with coordinates is both 0 cannot enter into this because that would correspond even to ideal 0 here. And that's not what we want. But otherwise, we just... And why there is 1/4 here? Yeah, because we are overcounting. Otherwise, there are 4. We discussed that. So, of course, when you look at it like this, obviously, this is holomorphic in real part of S bigger than 1. You can just use simple calculus to prove that, right? For real part of S bigger than 1. But the question is why it can be analytically extended to now, let us introduce the theta function. Theta Z2 of t to be equal to sum exponential of minus pi n squared plus m squared. Now, n and m belongs to Z2 t. You see, that's the analog of theta function for this two-dimensional lattice, right? Integer lattice. Every point on the integer lattice contributes a term to the sum, to the theta function. And obviously, this sum is convergent if t is positive. It's obviously convergent, for t is positive, and yeah, that's a very nice sum, right? And you see, it's an analog of the one-dimensional lattice function, which is we had as a subset of R, right? I mean, before we had like Z. Here we have Z2. I mean, here we have theta function, and for this also we have theta function. Each lattice has its own theta function. So, and one way to study lattices is through the study of the zeta functions, because lattices are very complicated objects. They're not easy objects, as you might think. Anyhow, but these are this is the integral lattice like this, and we define. Now, this, of course, is a very simple theta function, because we can write it in terms of the old theta function, right? What is that? That's equal to sum e to the minus pi n squared, n in z, times sum e to the minus pi m squared, m in z. I mean, that's kind of clear, right? Oh, t, yeah. Yeah, that's m squared, obviously, right? I mean, that's clear. We just multiply like that, yeah. But this is like theta, so this is equal to theta z of t squared. That's theta z of t squared. So from this calculation, you can see that this lattice z2 theta function has a different modular property now. So this has like, what is theta z2 of t in terms of 1 over t? This becomes equal to 1 over t, actually, theta z2 of 1 over t. This is the modular property. You see, we had this before, 1 over square root of t. We had 1 over square for usual theta function. But we are multiplying two of them, so we pick this term now. And the reason this is 1 over t has to do with the fact, obviously, that this is a two-dimensional lattice. The other one was one-dimensional. Each dimension you go, you add a factor of root t in the denominator. Basically, that's how you go. Question? Okay, so this is the modular or functional equation for theta z2. Functional equation for theta z2. And you know what was Riemann's idea? So Riemann used the functional equation for theta to prove analytic continuation and functional equation for zeta using Mellin transform, right? So we are going to use the same trick now. And it's always like this. You always introduce a suitable theta function. You prove its functional equation or modular, its transformation rule. So basic idea is how t and 1 over t are related, the theta values. And then you get what you want by using Mellin transform. So let me now go on and tell you. So is there any question?
There are other extents.
Yes. If you go to like, it depends on how many basis elements you have, B1, B2, Bn, right? So if you have like a third degree extension, you need 3 basis elements. Yeah, always works out that way. Yes. Yes. And because there is this lattice inside the ring of integers of any number field, and that's your that's where you work. Yeah, that's right. Yeah. So it's very much like working with tori, a spectral geometry of tori. Yeah. All right. Now, so what do we want to do? So next we use Mellin transform. Next, use Mellin transform to relate what to what? zeta to theta, right? To relate zeta ks to theta z2 of s, of not st. Is this one, right? So now, but the basic Mellin transform is lambda to the power minus s equal to 1 over gamma of s, right? Integral from 0 to infinity, e to the minus lambda t, t to the s, dt over t, right? This is true for real part of s positive. Then we just let s equal to, I mean, basically, yeah, what we want to do, we just take, yeah. We just sum, but we just don't want just m, right? We want m2 plus n2 for all m and n, because this is, we have to have our eye on this. We have to produce this zeta. So put m2 plus n2, right? Exponential of minus m2 plus n2, t to the s over t dt. Now, obviously here, m and n cannot be 0, both of them. This is, so, and then we sum over all m and n, right? If you sum over all m and n, you get sum 1 over m squared plus n squared to the power s, which is your zeta function. So this is equal to 1 over gamma s, integral from 0 to infinity, sum exponential of minus, I mean, this is prime, sum exponential minus m2 plus n2, t to the s times t to the s over t dt. This is all, again, I mean, this is, again, is a restricted sum because 0, 0 is excluded. But we have to bring it into the game because in the theta, 0, 0 is included. So we have to bring that to the end. So you just do that by adding 1 and minus 1, and then you go from there, right? So what we did in the case of Riemann zeta function, what was the next move? Change variable t to pi t, so that you would produce here exactly terms like theta functions. But there is also this term 1 missing, so we just subtract 1, add 1 to compensate for that, and then we go from there. So from here now is exactly similar to Riemann's proof of analytic continuation and functional equation for his zeta function. I mean, what he did in the second proof is like a blueprint that is just repeating in many guises and contexts. Okay, so I'll be very brief. I don't want to write all the gory details because we went through it once in the case of zeta function, but anyhow, so yeah, okay. So let me write it like this. Maybe I just put 1/4 because we are interested in 1/4 of this sum is equal to 1/4 of this. Just multiply by 1/4. And then you change the variables. So you get, what? So zeta qi Gaussian rationals S, you get equal to pi to the S at pi to the S, because we are changing t to pi t. So you're going to pick up the factor pi to the S over there, right? Pi to the S over gamma S. Integral from 0 to infinity, theta of theta z2 of t minus 1 over 4 t to the S dt over t, right? So then, all right, so now what? So write the right-hand side. So sorry, theta? This is minus. This is not in the power. Is that what you meant? Yeah, it should be down. Yeah, minus. Yeah, that's fine. Good. Yeah. Yeah, so write it as integral from 0 to 1 plus 1 to infinity. And this integral, you change it into this by doing change of variable 1 over 1t and using these theta transformations, using that theta z squared, t equal to 1 over t, theta z squared of 1 over t. So if you do that, you are going to get this term on the right-hand side, but you change it again to theta z2 by using this. So it's exactly like what we did. So at the end, then you prove that. So now then let zk, qi of s, this is the completed zeta function of Gaussian integers, right? Completed zeta function of Gaussian integers. So this we define to be pi to the minus s, gamma of s, zeta k of s. Now you see the difference with the completed zeta function of Riemann. In that case, we had pi to the power minus s over 2, gamma of s over 2 times zeta. But here we have pi to the minus s, gamma of s, exactly because the transformation rule changes. So the way that this theta function behaves dictates, this, you go through this tells you how to define the completed zeta function. Okay, so, and then the functional equation comes out zk s equal to zk 1 minus s again. Now we just, this is really proof for k equal to qi so far. Nothing more than that, of course. Just for this case, right? It's exactly the same. This proves functional equation and analytic continuation more or less at the same time. So that's the question. Yeah, this is again the conjecture is that all non-trivial zeros are going to be on the line real part of s equal to half. So you have Riemann hypothesis for these ones, which is of course still not proved. No, nothing, none of these things, none. for Dedekind Zeta function, and also for L functions, I'll discuss. We have conjecture. There are conjectures. None of it is proved. Yeah. Well, the only cases that's been proved is for Zeta functions over finite fields. This is not easy. I mean, this was done through a series of steps by Artin, Hasse, Wey, and then finally Deligne. These are Wey conjectures. Yeah, well, as a result, yeah, the proof of one of Ramanujan conjectures about the bound, Ramanujan bound on the value of his tau function was proved indirectly. Yeah. Oh yeah, yeah, you mentioned something else. Sorry. Yeah, for graphs also, yes, yes, and for Selberg zeta functions, yes, yeah, for Selberg zeta function, yes, that's proved, and yeah, so that measures the lengths of geodesics in terms of the spectrum of Laplacian. So I will give this course next winter, the coming winter, spectral geometry. So it'll be all about this. Yeah, doing this sort of spectral geometry over compact Riemann surfaces and even non-compact ones. So it'll be all about this thing. Okay, so now, so where are we now? Okay, so I mean, if you want, we can just write this functional equation in some, I don't know, because yeah, just a second. So I will have, I'm going to write it pi to the minus s, gamma of s, zeta k of s is equal to pi to the power minus 1 minus s, gamma of 1 minus s, and then zeta k of 1 minus s. Okay, it's the same thing as over there. I just wrote it in explicitly. Again, for k equal to qi. Okay, yes. Who was that? Yeah. Yes, there is a formula. There's a functional equation for any number fit. I mean, in this case, first of all, the fact that so let me give you an example of theta functions. So imagine you have a lattice Z3. So let's look at this theta function. This is sum m n p. Okay, 1 over m squared plus n squared plus p squared to the power s. Huh? Oh, that's why I was worried that this sum is not in good shape. Yeah, sorry. Sum exponential of minus pi m squared plus n squared. Plus, I think we have to call it off now. P squared, yeah. M and n p belong to Z3. Oh, times t, yes. Yes. Yeah, so now, obviously, this is convergent for t positive again. And of course, in this case, quite easy. I mean, is theta z t to the power 3, right? So the functional equation in this case, there's a factor of 1 over root pi to the power 3 mixed up. So theta z3 of t equal to 1 over root t to the power 3 theta of zt of 1 over t. And that's the only difference. So this will dictate how to correct your completed zeta functions here. It will tell you what to pick here. So what we should pick here, I'm not sure. So it will, yeah, if we go to to the Mellin transform of zeta to get theta, we'll see what factor of pi, for example, you have to pick up. I believe it should be minus 3 over 2s and gamma of 3 over 2s in this case. Because it was like gamma of 1/2 s, gamma of 2/2 s, and a gamma of 3/2 s. So that's that one. But the rest is the same. Yeah, this is the, so yeah, exactly. So yeah, that's a good question. Is it only degree of extension? Is there nothing else in the functional equation? Yeah, someone should check in Wikipedia what is the functional equation for Dedekind zeta in general. It looks like we just rely on degree. I mean, is there anything else involved? Yeah, but yeah, that's right. But norm, yeah. In this case, norm is simple, is A2 plus B2, but in general may not be that. Oh, yeah, yeah. The extension is like Q of... Yeah, norm could be A2 minus B2, A2 minus 5B2, for example. In that case, then it's not so easy. Yes, yes. No, it's much more involved. Yeah. 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 Yes. The lattice, though, I mean, because it's an integral lattice, so it's always like we can just take, because this B1, Bn, or just fix it on. Okay, so I'm not going to go into. Is that right? So is there anything beyond the degree of the extension involved? Yeah. Oh, the discriminant comes. Ah, woo, woo. Yes, that 1/4 is related to discriminant. Okay. Okay, you're out of luck. You have to study that. No easy solution here. Yeah. Okay. So what I wanted to do next is to, yeah. So the last thing, let's see if it's worth spending time now. So I wanted to use this to compute the value of this guy at s equal to 0. Yeah. So let's see if we can do that. So the question is this now. So let's look at, again, we are in the case of k equal to qi. So zeta k s, we know that it's regular at 0, right? It's regular at 0. And the question is, what is zeta k at 0 equal to 1? We know that it has a residue at 1. We know that. Is it one of the assignments? Is it for tomorrow? I mean, the assignment due for Thursday? I see. It was also at 0. Okay, so should I not do it then? Or? I'm not saying not to. I'm just letting you know that. Oh yeah. Well, thank you. Yeah. Well, let me do it now. Well, I'm not sure I can do it. Let me try. I don't know. Let me try. So, so this, what is that? What is this residue? You remember? We did it this morning. I mean, just an hour ago. It's pi of 4, right? So can we compute this now? Now remember, I mean, this originally for real part of s bigger than 0, at least, I mean, this is like, we had this factorization, right? This is zeta q of s, the Riemann zeta, times L sky, and L sky was 1 over 1 to the s minus 1 over 3 to the s plus 1 over 5 to the s minus 1 over 7 to the s and so on, right? And the problem is we cannot calculate this at s equal to 0 because it's given by a different formula. This has an analytic extension, but we don't know what that formula is. You cannot put s equal to 0. You get 1 minus 1 plus 1 plus minus. It gives you nonsense, right? So we cannot use this, but we know zeta q at 0. This much we know. What is the Riemann zeta function at 0? Well, I ask you to calculate. What is it? Minus half. Okay, so let's use that. Then how can I use this functional equation to calculate this? You can do that, right? You just sub in, because if you sub in s equal to 0, you're going to get pi to the 0, gamma of 0. There's a problem. Gamma of 0 is problematic. Zeta k at 0, that's regular. We want its value. But this is a problematic term. But this is equal to pi to the power. S is equal to 0. Is it minus 1? Yeah, why not? I don't know. Gamma of 1. You know what is gamma of 1? It's just 1 because it's 0 factorial, which is 1. So this is 1. And then zeta k at 1? Yeah. Yeah, that's also problematic because there's a residue. So what you have to do, you have to take residue of both sides. You have to take residue of both sides. I mean, not this one, put s. So basically, you have to compute residue of this at s equal to, both sides at s equal to 0. But then there is something funny happens. So I won't do that because you have to be observant of something over there. Otherwise, you get the wrong answer. I won't do it then. Okay. Because this is exactly, as you said, is similar to your assignment. But that's what it is. The only thing is you have to be careful when you compute the residues. Okay, I think I'm going to call it off for today. So, but we can discuss. Okay, now it's good. Looks like it doesn't want to end.
I don't know what to do. This
Okay, is this ending then? End for all. Okay, guys, thank you. Yeah. Yeah, I think instead of reading the general proof, it's better to build the understanding in a case by case.